All right, this problem says determine the range of x values for which the third degree Maclaurin polynomial for e to the x approximates e to the x with an error of at most 0.01. Write each number in the interval to the thousandths place. Okay, so this is a range of x values means we're going to use a graphical technique, or at least that's what this problem was implying. So the way to do that, let's first write down our third degree Maclaurin polynomial for e to the x. So remember, e to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial, etc. Now we're going to use the third degree, so we're going to truncate here. Right, we're going to use that. And once you do that, it's an approximation, which means there's an error. Okay, so my third degree Maclaurin polynomial is this. Okay, and so now what I'm going to do is I'm going to graph the error. So remember, we have different notations for the error. We could say this. We could say this. This is a good one because it's describing a difference between these two outputs. Okay, so I'm going to graph this, right? I want to graph this into as one of my equations, and then I also have to graph this. Okay, that'll usually produce some picture that looks like, it's going to give you some graph that looks probably something like this, which you'll see in a second, but it's, some like U-looking graph. Okay, there's our error. Okay, so that there is this. The error is going to be exactly 0 at the center. These are both centered at 0, so they're going to agree there. And then when I graph, y equals 0.01, I'm trying to figure out where the error is below that, and the error is below that in between these two x values, which we're going to go find. Okay, so I've already got it set up. Let's just go to the calculator, split view. Okay, so look, I've gotten to what, basically I've got, the way I do it is I break it up. I got the function, I got my polynomial, and then I've got the error in y3, and then I've got 0.01 into y4. I unhighlighted y1 and y2 because I don't want to see those graphs. I just want to refer to them. I wanted to refer to them to graph this. And then for my window, my x-min and x-max, I just figured it's probably somewhere between -1 and 1. Because that window's pretty tight around x equals 0. Remember, the errors get worse the farther away from 0 you get. And then the y min is 0 and the y max is 0.02. That way my 0.01 over here will go right through the middle of the screen. So I hit graph. Okay, and so now that's exactly what we're looking for. I have to find the x values of the intersections. So I'm going to hit second calculate. I'm going to hit 5. And this is a little bit different calculator probably than yours, but use whatever your calculator does. All right, and so there's the intersection. It's the first one is x equals negative 0.72453. I'm going to round that to negative 0.724. Okay, because if you kind of truncate it there, you've moved a little bit closer to 0, where the error is still going to be below 0.01. So I'm going to put negative 0.724. Now I think if you're in my class, the one we did in class, we used symmetry. But that was because we did the sine example. E to the x is not a symmetric function. So you really do have to go calculate that other intersection point. It's not going to be positive 0.724 in this case. That was just because of the symmetry of sine. And I got an add. And I'm gonna, sorry about that. I have to pay for the free version, I guess. I mean, the paid version. Hopefully that wasn't too distracting. All right, so I'm going to find the intersection over here. Enter. All right, so that's 0.675, we'll say. Okay. You can use hard or soft brackets on this because, once you truncated, both of the things you write will be true, whether you include those endpoints or not. I think I accept it. And if you do this problem in Delta Math, it should accept that. All right, hope that helped.